Hi everyone, welcome to this early morning preview session. We're just going to get started, kick things off with program analysis and parsing.
Okay, thank you. Hi everyone, I'm David Pichardie. I will present you the session Program Analysis and Parsing. We have 3 papers in this session. The common topic is a bit unclear for me. It's more program analysis, static analysis, and dynamic analysis and parsing. So I will split my talk in 3 parts. And we will start with the first paper, which is about SSA translation is an abstract interpretation. So it deals with SSA, so a bit of background on SSA form. It's an intermediate representation that was introduced in the 80s, and it's very, very popular these days. It is used in GCC, LLVM, all modern JIT compilers rely on that. And compiler designers, they like this representation because it gives them very strong invariants. I will define them just later. And it makes their life easier because it's more simple. They design simpler optimizations like that. And also, it's a very efficient representation. Efficient in the sense that you can obtain SSA representation very efficiently. We have almost a linear algorithm for that. And you can even use SSA during register allocation when you go out of SSA. So compilers love SSA. What is exactly SSA? So it means single static assignment. So the purpose is clear. You want each variable to be assigned only once. So if you think about it, it's quite easy to do on straight line code. So for example, if you have this straight line code here, this one is not assigned once because x is assigned twice, but just by renaming the variable, you can obtain the SSA form very easily. But with join points, it's a bit harder because look here, k is assigned twice, but how to explain that this k is either this one or this one, just with single assignments. That's why you will need an extra instruction for SSA form, which is the famous or infamous phi operator that you will put at the beginning of the junction point, and it has a very specific semantics. It means if you reach block L3 coming from block L1, then assign key 1 to key 3. Otherwise, assign key 2 to key 3. Okay, so it's a very specific operator, and but with this form we can do a lot of interesting optimization and static analysis very efficiently. But there is a problem. In static analysis and compilation, we know we have a phase ordering problem, which means transformations can help static analysis. For example, SSA help constant propagation. But also static analysis can help transformation to do a better transformation. For example, an alias analysis may help you to transform differently your program, even your SSA form. So you have to choose an order, and it's difficult. And in fact, the optimal order is to iterate all this chain, which is a bit inefficient. So in abstract interpretation, there is a folklore theorem that says you should not do that. You should do all your analysis at the same time, combining all the analysis, what we call abstract domain. So this notion of abstract domain product is very interesting in abstract interpretation. And that's why it's very interesting that in this paper, the author is turning SSA translation into an abstract domain so that we can combine it with other analysis in an interesting way. That's the first paper. The second one is about data races. Okay, what are data races? Well, you heard about it a bit yesterday. It's a fundamental issue in multi-threaded programming. It leads to tricky bugs, very difficult to reproduce, to test. And it's a very, I would say, mandatory property. in fact, you can decide. If you have a multi-threaded program, if it contains data races, and I will define what it is just after that, well, if it has no data race, then you are fine to reason on your program using an interleaving semantics. Okay, you just interleave the execution of each thread, which is what you could expect. But if not, well, you have to deal with this notion of weak memory models that Victor Vafeidis explained yesterday. And I would say you would rather be an expert. Okay, so if you are not an expert, you don't want data races. And so you will need to check if a program is data race free or not. Before explaining that, let me explain what is a data race. In fact, there are two ways to explain what is a data race. The first one that I have used just before is a bit operational, is the fact that during executions, we don't want two threads accessing the same location at the same time when one of these access is a write. We say we have conflicting actions. So this is a definition that is really easy to understand in an operational way. But there is also an axiomatic definition that is quite useful, you will see. So just an example, the operational, so if we have an example like that, so x and y are shared variables, they are initialized to 0, and then we start two threads, here and here, and R1, R2 are local registers. If we want to check the data race freeness in an operational way, we will have to consider all the interleavings. And there are many of them. And in fact, this program is really bad because in all of them, it has races. But it's a bit too long. With the axiomatic model, you will get one diagram for every traces. The idea is that every memory action will be put in a partial order world. This notion of happens before. So just to define what it is, we will say that two actions are in the program order if they are in the same thread, and the program gives us this order. Okay. Otherwise, we will use the synchronization like thread spawning. And combining these two partial order, we obtain the happens before partial order, and we define data race as conflicting actions that are not, it was explained here, sorry. Conflicting actions that are not in happens before relations. So this is another way to look at this notion. They are equivalent, and this is an interesting way, I will skip that, because it can help you to design a dynamic data race detector. Okay? And in fact, you can do it statically, but it's quite complex, and you will have false alarm, of course. But dynamic detection is very interesting. Big problem is computation cost, but with this paper, you will see a very, very efficient randomized algorithm. Last, it's about parsing. The idea is, generally, you learn that you should not use ambiguous grammar when you do parsing, except that, so it's an example in Python. This is not ambiguous because the grammar in Python has precedence. But the problem is that C use another precedence, and nobody remember what is the precedence of these operators. So maybe another approach is to allow ambiguous grammar, but make sure that the programmer will always be able to resolve the conflict. And this is explained in this third paper about parsing. That's all. Thank you.